Welcome back. Last time we talked about the first law of thermodynamics and applied it to our simple steam engine. Later in this video series, we will take a more in-depth look at steam engines and other similar devices. For now, I'm going to repeat it until you're sick of it. In minus out equals change. Energy cannot be created nor destroyed. It can only change forms. In minus out equals change. So, imaginary students.
Hi.
Let's talk about the forms of energy, shall we? What are some types of energy?
Kinetic.
Okay.
Potential.
Right. Fire. Not quite.
Heat.
Thank you.
Fusion.
Not bad, but not exactly what I had in mind.
Solar.
Technically, that's heat.
Work.
Correct. Caffeine. Definitely not.
Oh, I know. The force.
Okay. Let's keep this moving. For this particular video series, we will focus on 5 general forms of energy: heat, work, kinetic, potential, and internal. Heat is sponsored by the letter Q, and internal energy is brought to you by the letter U. This is typical for most thermotexts. What is not typical in a thermotext is a dry sense of humor and absolutely terrible graphics. Fortunately, we have plenty of both. From your studies of physics, I hope you are familiar with kinetic and potential energies. You should recall that kinetic energy is based on the speed of a particle, and potential energy, specifically gravitational potential energy, is based on the work that gravity could do to a particle. These are what we call macroscopic energies. They are dependent on the frame of reference. For example, consider this. Is the red dot on your screen moving?
Sir, I don't have a screen.
Sure you do. It's at the front of the imaginary classroom.
Oh, okay. Thank you, sir.
So, is the red dot moving?
No.
Well, think about this. The dot is on your screen, which is on the Earth's surface, assuming you're watching this video on planet Earth. So again, is the dot on your screen moving?
No.
I am so glad you volunteered for this demonstration. Let's try this in a different location, shall we? Let's pretend you were able to observe this dot from the surface of the sun.
No.
Now, does the dot appear to move?
Yes, quickly.
So, again I ask, is the red dot on your screen moving?
Relative to what?
That is the correct response. Relative to an observer on the sun, the dot is moving quickly.
Yeah, it's still moving. It's really hot out here.
However, you may be unaware of that motion, since you are most likely moving with the same speed as your screen. Macroscopic energies like kinetic and potential energies depend on who or what is measuring or observing the motion and position. In some frames of reference, an object may appear to have no kinetic or potential energy, but the same object may appear to have massive energies relative to other frames of reference.
Still moving. Can I come home now?
Now, those of you who do not have ADHD are probably asking,
Steve, seriously, why do we care?
well, here's the truth. Our goal is to understand the first law. In minus out equals change. Kinetic and potential energies are types of energy that can change. Typically, what we really care about is the change in kinetic and or potential energy. In physics, we would have talked about adding work to an object, which can change the kinetic and or potential energy of that object. However, if I add heat to the dot, it probably doesn't change velocity, so the kinetic energy doesn't change in any frame of reference.
No, still the same speed.
And it probably hasn't changed in elevation, so the potential energy hasn't changed.
No, still the same spot.
But, according to the first law, the addition of heat will cause an energy change for this scenario. What we find is the heat into the dot is causing a change in the dot's internal energy. Internal energy is often referred to as a microscopic type of energy. This simply means it is not a function of the frame of reference. So, unlike macroscopic types of energy, internal energy is not dependent on the motion or behavior of the entire object or system. Instead, internal energy represents energy at the molecular and atomic levels. It represents the energies of rotation, vibration, and motion of the molecules and atoms, as well as the energy in the bonds between them. I think it's important to point out I am not an expert in molecular physics.
Did an engineer just admit they're not an expert in everything?
It happens occasionally. Look, what's really important is that we understand the definition of internal energy, but we don't have to be experts in molecular physics to estimate changes in internal energy. Ultimately, the main topic for many of our future discussions will be internal energy changes. For now, let's revisit the first law. We have three forms of energy that can change: potential, kinetic, and internal. Also, there are two types of energy that can be added or removed: heat and work. Therefore, the first law of thermodynamics, energy in minus energy out equals change in energy, can be written in the form heat in plus work in minus heat out minus work out equals the change in internal energy plus the change in kinetic energy plus the change in potential energy. This is what we call the first law of thermodynamics for closed systems. In the next video, we will demystify the concept of systems. For now, it's more important we make it uncomfortably obvious how the first law equation works. The left-hand side of the equation represents energy added or removed, and the right-hand side represents energy change. So, to repeat one more time,
No, sir, please not again.
in minus out equals change. Until next time,
Hey, don't forget me. Can I go home?
hey, thanks for watching. If you liked it, give us a thumbs up, subscribe, and don't forget to follow us on Facebook. Stay tuned, there'll be more videos to come.